to get you a better understanding of it, because it's a critical concept that's difficult to get across. And so I'm going to talk about right now, to start out the whole thing, with random variables. Okay, so what is a random? And then we call it a random variable. So when I'm asking for a probability of, let's say, some kind of random variable, let's call it x, right? And I want to know what x is. Let's see, what's the probability of x equal, I don't know, say 3, for example. 3 of whatever. Okay, this guy here, this x is called a random variable. Now, when you hear the word random variable, well, the word random means what? Anybody? What's random mean?
Not sequential.
You never know. So let's supposing that you have a sample. So here's what you're trying to get to know. That's your population. And here's your sample. Notice it's smaller. Okay, and then do you recall that we start building some kind of histogram? Yeah. So I'm building some kind of histogram with the idea of trying to figure out that there's a machine in here. There's a machine in this process. Okay, so imagine that we have this machine, and this machine has some processes by where it's generating outcomes, x of 1, x of 2, just keeps generating them, right? So what I'm trying to get across is that if you have an event, if you have a process that's truly random, you're lost. Basically, just flip a coin. Because a histogram of this sample space would look like, if it were random, maybe it would look like this is a bar here, and then this one would go right here, and then when this one goes here, there just doesn't seem to be any rhyme or reason. Do you understand what I'm saying? So there's a process by which this thing is generating so many, remember, so many frequencies fell into this bin, so many in here, do you remember? And if I divide by n, which is the sample size, then I get probabilities, estimated probabilities, right? So if I get this, for example, if I wanted to graph the winning numbers of the lottery, if there was some bias in the machinery, then I would expect to try to find some structure and not something just totally random, okay? If it's truly random, you can't do any prediction because it's all the past data that you're looking at is totally random. So you people, spend a lot of time developing random number generators to just like throwing the dice, maybe, but with a computer program. There's always a question is how random can something really be if you're built a program to generate randomness, okay? But that is a random distribution. It's not even a distribution because it's all over the place. Remember, normally we're used to seeing what? Something that's more bell curve, right? Or any other kind of shape. This indicates that this blocks that we know nothing about is churning out results randomly, only to the extent that it's randomly being generated from a shape like this. Do you see the difference? This has some structure inside that we're trying to figure out. The data itself is trying to tell us that inside of it is a structure. And although it's popping up these variables and we don't know exactly what they're going to be, thus the name random variable. Because remember, in algebra, we get to pick the x and then we figure out what the y is. No, it's this process that's generating up the x's. And we want to know about that process. Because once you know the algorithm of how this process works, yes, then we can work our way over to doing predictions. Because we know there's a structure. Right? So let's see if somebody else can tell me now. If I say random variable, I'm not necessarily talking about a process, a box. It's truly shooting out events or outcomes randomly. Do you follow what I'm saying? I don't know if I got it across. Let's see. Somebody else tell me in their own words. Who wants to volunteer? What's the difference between a random variable and a truly random process? You see, if this was truly a random process generating out x's, and we were wanting to ask what's the probability that you're going to get 3 as an outcome, for example, right? if the process was truly random such that it generates this kind of histogram, then we have no prediction abilities of assigning it a probability. We only have it if we see that the histogram is indicating that this has a shape which is helping predict what the true process is of that box. Does anybody know what I'm talking about? Not all at once. What does it mean to be truly random event? It means there's no predicting ability. It's white noise. You get that in all sorts of engineering. You have satellite telemetry. You have noise to clarity, like if you take a photograph. Astronomy, you got such fuzziness. The filters that you try to run it through are in order to cull out and find out what kind of process it's generating, and you can actually improve the photograph by noise discrimination. But if a process is truly random, that's what it means by definition. It's truly a random event generating thing, right? No? What does random mean? Random means it's just outcomes are popping out. But not everything that generates outcomes has a pattern behind it. If it did, then you could manipulate it towards your advantage. That's why people are trying to do this kind of thing with lotto numbers. Now, let's say I got the lotto going, okay? Now, here's a good example, I think. If, let's say that the ink that goes on the ball with the number, let's say, yeah, and let's say a double-digit number, right, of the ink might change slightly the weight of one over the other. If one had just a 1 on it and the other had a 50 on it, right, we're going to say, well, there might be some structure generated because the balls themselves are not exactly perfectly random, right? Because you put an ink on there and it's starting to put some balls heavier than others, okay? Now, if it's the case that the ball with more ink on it is going through some kind of generation, you know, as you're shaking up the balls, right? And then one shoots up, right? If the system has structure in it, right? And you figure out that structure, that's going to help you predict a winning number. That is that the ink itself is causing a structure, an internal structure of the data. Do you see? It's actually causing a structure, a certain habit, things are popping up, but they're popping up at a certain frequency, right? And so if you find that it's popping up, numbers are popping up, particular numbers are popping up more than others, you've just discovered an internal structure within the lottery system, which the lottery people don't want. Because if you figure it out, you know what I'm saying, it changes the payout. Okay? Now, how is it supposed to be? It's supposed to be that the ink on 1 is insignificant to the ink on 2 digits. So that when you're generating it, right, the balls are popping up, totally random. It's just as much chance as one coming up as the other, and then you never know, right? So you can play with it all you want and think you found a structure, but it's probably noise. Now, the more noise, the more fair this game is, right? It's like if you're flipping a coin. What does the law of large numbers say? Well, if it's a fair coin and you keep flipping it trial after trial after trial, and you see that the number of heads and tails will come out to be about 50-50, right? So if it's not fair, if there's some defect in the coin, right, then it's generating a pattern of defectiveness, sort of. In which case, even after long things, you start saying, hey, this thing is a biased coin because it's landing more on one side than the other. Do you understand? Okay. So when I'm talking about random variables now, I want you to consider that, yes, that means it is a variable that we can't really know exactly what it's going to come out, but it's going to come out according to this distribution. Do you understand? The confusion is when I say random variable, random to me means it's an outcome, but no, it's an outcome with a pattern. And that's why we take our sample and we look at the histogram to see what this thing is most likely doing. We can't test the whole population, but we can test the sample and then look at its distribution. The concept of random variable itself is not all that easy. Okay, now, having said that, then we can look at our probabilities, because we're going to be calculating these things. The probability of event happening, okay? One thing that you'd like to know before you do that is how is the structure distributed, right? Because once you figure out it's probably coming from this kind of distribution, then we can come back and use that curve, that distribution, to calculate the probability under the curve. Are we okay? Okay, now, before we did that, we talked about different rules of how to do the math of probability. One is the multiplication rule of two events happening, two or more. Okay? And the other one was what? The addition rule, correct? So again, I'll use this as my little chalkboard. So if I'm asking about event A, do you remember this hump like that means and? All right, and event, well, let me get rid of this. If I want to talk about, if you will, you can think of it as the intersection of two events, okay? Now, the question is whether this or any one of these is causing an effect on the other. If it's not, then we say that A and B are independent events, okay? So if they're independent, you will find this result. You can multiply them. Okay, that's how you would do the multiplication rule. This is in the case that they are independent. What would you do if they're dependent? If they're dependent, it becomes a conditional probability because this guy might be affecting this guy. Remember when we're drawing two cards? If we draw the first card and we don't replace it, we've just affected the second card, right? So to calculate this one, this is the case of independence, right? But in case of dependence, then the probability is A, given that B has affected the outcome of the next draw. Okay, and what this is for dependence, okay? And that's going to be equal to the probability of A and B occurring. All right, this is a conditional probability given that this has already occurred. Okay, so whatever's behind the bar is going to be here in the denominator, and it'll also be in the intersection of the two events. Okay, this is the concept of independent and dependent events. Different when I'm doing the addition of probabilities. So now, if I want to talk about two events happening, I can say the probability of, look at this one now, it's not and, it's or. Do you see the or B? Now that means one or the other. Correct? So what we do, we add the probabilities, right? Not multiply them. Here, when we had an intersection, we multiplied the probability of this occurring and that occurring. That's a B, by the way. It's an ugly thing. But here, now we have the question of, if this is equal to this, if this is true, do you see? That's the addition rule of it, and it comes in. Now, this would only occur if the two events are mutually exclusive. They're not overlapping. It's a difference in independence. We're not asking whether this caused this other one right now. I'm asking whether this is the case, all right? This means, right, that you're mutually exclusive event, okay? If it's not, if you have this is the case of mutually exclusive. You have event, there's a group in there that's there, and here's event B, and there's no overlap. One's not on top of the other, right? So then it would be just this, okay? This is a case of a graphical case of mutual exclusivity, right? Because now, if I have this case, okay, so I have A, B, and then I have an intersection of A and B. You see it? So in the case of being not, this is mutually exclusive, but this is not mutually exclusive, in which case we have to say P of A or B is equal to, again, the P of A like we had before, plus the B of B, but we have to subtract one intersection of P, A, and B because we've counted it twice, okay? Now, I drew a picture here. This is not, mutually exclusive not, okay? This is mutually exclusive, right? But I can't really draw a Venn diagram from this because I'm talking about whether one event help change the outcome of the next. So I can't really draw it. It's the structure of the experiment itself or the process. Is this okay? Okay, so let's now that we got that under our belt, let's take a look at this homework thing. And that was on, we were on 4.2 or what section were we on? Yeah, 4.2, 4.3, and 4.4. I left out 4.5 because that has to do with simulations. It's kind of cool, but I don't know if it's worth it at this point. Okay, so we need something like in here, let's say one. Let's try this here. Okay. And we went over if you have an event A, yeah, everything that's not A is A not. So if you take A, right, you should be able to see that if I take the probability of A occurring, yes, plus the probability of A not occurring, I hope you can see that's 100% because I've taken up the whole area. I've added the area of the circle and the area of the circle not, right? So that means that you can do anything you want. You can do your algebra here and say P of A is equal to 1 minus P of A naught. Did you see I just subtracted a P A naught from both sides? Okay? Could I solve for A naught? Yeah, I could. I could just subtract one. I mean, I could subtract P of A over there, right? So I can have another way of writing this is P of A naught, right, is equal to 1 minus P of A. Because we know there's nothing else. We've added everything up in the sample space. Remember, this is our sample space. I'm not talking about the population. Are we okay with this? Is it too easy? I like this class. Everything's easy. Okay. Yep. We talked about this skydiver stuff. And that's not what I want. Okay, the additional rule. All right. Okay. This is or. Remember that this thing is, another way of writing the word or is A or B. That's the logic symbol. Okay, so when we're talking about the addition rule is that, okay, a single event A occurs or an event B occurs. If one or the other occurs, guess what you're going to do? You're going to add the probabilities of A plus B, yes? Unless there's an intersection. Notice that that's and, not or. And is the intersection of those two circles on the Venn diagram, right? That would be the probability of A and B. This becomes the multiplication rule. So when we have or, we have the addition rule. When we have and, we have to take into account the multiplication rule. You see now? Now, if you have or and there's an overlap, then you're going to have to subtract this intersection, yes? If it's an and one outcome affects the other, you have to use the conditional probability of A given that B has affected what A will come out to be. That's called a conditional. Yeah, and it's going to be the probability of the intersection occurring, yes, divided by the probability of B occurring. That should be in our next section here. That's the addition rule. Okay. So I guess they're going to talk about. Let's go to the next. Okay. When I drew that picture of the two events not overlapping, right? It's called a disjoint or mutually exclusive because they're disconnected. It's okay? Okay, let's try some problems here eventually. This is something I went already, that the probability of A plus the probability of A naught is equal to 100%, and these are just algebraic manipulations of the same equation. Okay? And now we talk about the multiplication rule. Okay. Okay, so here's another one. Event A occurs first. Okay. Do you see that that occurred first? That's like drawing your first card, yes? You look what it is, but you don't replace it. Your next draw now has been affected because the sample size n is one less. Yes or no? Okay. So in that case, since that occurred first, this occurred first. A, oops. Yeah? Okay. Okay, A occurred first, right? Since that occurred first, I'm going to write this like this. The probability of B given that A happened first. Do you see the difference? What happened first comes after the bar because it's the given. Given that this affected the outcome of the next. You understand? So that would be this. You see the probability of A given not now. So when we want to look about the if it's a random event, that this itself is equal to the probability of B and the intersection of A. Oh, yeah. But I divide by the probability of A this time. Why? Because it happened first and that affected the next outcome. Whatever is affecting goes on the denominator. Okay? Now, how about if I want to test to see if it is? So suppose that I do this. That I say this. The probability of A and B actually comes out to be the probability of A times the probability of B. If that is the case, then we're talking about independent events. One's not, that means you're replacing the card before you draw the next one. Okay? But if this is equal to this, okay, now I'm going to take P of A, right? And I'm going to multiply it times P of B given A has occurred. Okay? So if you do this calculation, which we know this part of it is that, yeah? If you do it and it comes out to be the same as this, all you're proving is that it's independent. I mean, it's dependent, but if it comes out to be the same as this, it's independent. So you could play around with this. Let's say, so if I have the probability of A times the probability of B, you know, and A over the probability of B, yes? Okay. However, I'm just pointing out, if it were statistically independent, how can I rewrite that? Well, that looks a lot like this, right? I just have the B and the A mixed up, right? So if it's truly independent, then you can rewrite this as P of A, yes, times P of B times P of A, right? Because these are independent, then it becomes just a straight multiplication rule divided by P of, what was that? P of A, right? I don't want this, right? Because A happened first. Do you remember? Yes or no? Because Does anybody remember that the A's down this time because A happened first, yes? And look at this, that divides out. And guess what I got? The same thing that you would get. If they come out to be different, that means this thing is conditional probability, and it's probably kind of, let's try some concreteness so that you can see what I'm talking about. Okay, let's see. We talked about negative and positive results. Let's see. Okay, so let's take this case just for example. Look at what happens. This, they're saying, is a process without replacement, right? So I know they're not independent events, okay? And then the first calculations accept the second probability must be reflect. So in this case, we have 49 results. 5 of them are negative, yeah? So when we took that person, we didn't replace them, you see? So then we have 45 over 50 times. Now look at this drop down to 49 because we didn't replace it. Okay. So we have the sampling with replacement or without. Simply drawing or putting back the card. Okay, forget that. Let's go, maybe we'll go to the homework here. Okay, so now we have three adults are selected, right? So if I turn the light out and I randomly pick out of you, by the way, when you draw your sample from the population, you really want to be as random as you can be. We really want to have a random generator help pick out from the population. If you don't, if it's not truly random, then you've biased it yourself by the way you've surveyed the people. It'd be like trying a piece of pie all in one corner.